Okay, a question was asked about section 2.2, problem number 39, and they talk here about the greatest integer function, which is something that pre-calculus and calculus authors, I think, just invented. They seem to make a big deal out of it, even though it really doesn't seem to show up all that often out there in the real world. It's sometimes also called the floor function. And before we can try to answer any of these limit questions here in number 39, we've got to understand what this graph looks like of y is equal to what is called the greatest integer not greater than x. So what we're basically doing here is we're taking any value here and we are rounding it down to the nearest or the first integer that is not greater than the value that we started with. So quite simply, guys, it's really easy when you put in an integer value of x. The greatest integer that is not greater than 0 is 0. 0 is equal to 0, but not greater than. The greatest integer not greater than 1 is 1. For 2, it's 2. For 3, it's 3. And let's go ahead and do a negative number 2. The greatest integer not greater than -1 is -1. So obviously there's a pattern right here, and this certainly looks a lot like the function y equals x right now. But that's ignoring what this function really does. Where this function really gets interesting is where you put in non-integer values in for x. So if we were to evaluate what is the greatest integer not greater than 1.5, well, 1.5 is not an integer value, so we're going to have to round that. Now that 1.5 is between 1 and 2, and it can't be 2 because 2 is greater than 1.5. We always round down with this function. So the greatest integer not greater than 1.5, we round it down to 1. The greatest integer not greater than 0.2, we would round that one down and get 0. All right, even if it was something high like the greatest integer not greater than 2.9, we're still going to round that one down to 2. It can't be 3 because 3 is greater than 2.9. So if we started plotting some of these points, we might start to see what's happening. Let me focus on this concept right here. Any number that we put into this function here, in between 0 and 1, is going to round back down to 0. That means that 0.2 gets a 0, 0.6 gets a 0, 0.8 gets a 0. Every value here between 0 and 1 gets a 0 until we actually get to 1 itself. So I'll put an open circle right there, and then at 1, that's when it jumps up and gives us this y value. Now, the greatest integer, not greater than any number between 1 and 2, is going to round down to 1. So we're going to have y values of 1, 1, 1, 1, 1. So again, this is going to be a horizontal line segment until we get to an open circle here at the point 2, 1, and then it jumps up to 2, 2. And now I'm hoping you guys remember what this graph looks like. It's sometimes called a step function because it basically looks like a staircase, just minus the vertical pieces that are called risers on your stairs, everybody, but nobody cares. Let's talk about what's happening between -1 and 0. If I were to ask you guys to consider the greatest integer not greater than -0.5, ask yourself this question: what two integers is this number between? And the answer to that is it's between -1 and 0. And once again, we round down. We can't say that the answer is 0 because 0 is actually greater than the input value. So we would need to round this down to -1. So that means that this graph doesn't look any different over here on the side, down in the third quadrant, than it did up there in the first. Okay, so now that we've got a sense, and I hope this rings a bell, guys, for what this graph looks like as the step function, we can focus on what's happening here. The limit as x approaches c from the left-hand side of this function. And they did make a point of saying in the directions, you needed to read this carefully, that c was any integer. The directions do end with calculate c for an integer. So let's think about what happens at our integer values. As x approaches 1, but we are talking about a left-hand limit here, guys. As x approaches 1, the y value that we are hitting here is 0 over and over and over again. As x approaches 2, the y value we're hitting is 1. As x approaches 3, we're hitting a y value of 2 over and over again. So every time we do that, whatever the c value is, our limit is always 1 below that. So that's our left-hand limit, I should say. All of these are being read from left to right. So if we're taking the limit as x approaches c from the left, our answer is going to be one integer less than c, which we would denote as c minus 1. Okay, now let's work on the second part right here. The limit as x approaches c from the right of the same function. So I'm going to switch to purple here for this one. So let's again focus on what happens here as x approaches 1, but now from the right. Now my y values are here. My y values, as I move from right back to left, are 1, 1, 1, 1, 1. It certainly looks like the limit as x approaches 1 from the right is 1. And when we look at 2 from the right, all of those y values are 2. As we approach 3 from the right, all of those y values are 3. So it looks like whatever integer c that we are approaching from the right, our limit then is just going to be the value of c itself. And the example C or problem C is a little bit goofy now. Let me switch colors one more time on you guys. We'll go to green for this one. The weird thing about C is they're now not asking you to consider a limit as x approaches an integer, but rather a decimal. 2.6 is obviously right there, almost in the middle between 2 and 3. So we're talking about what happens as x approaches that green dot from both directions. And if we zoom in real tight on what's happening from the left, everybody, and by the way, I should clarify, since there is no plus or minus right here after the 2.6, we're actually talking about a two-sided limit here. So as we approach 2.6 from the left, our y values are 2, 2, 2, and 2. So it looks like our left-hand limit is 2. As we approach 2.6 from the right, we're right here, and once again, those y values are 2 over and over and over again. So since the left and right-hand limits agree with one another, we can say here that the two-sided limit, as x approaches 2.6 from both sides, is just plain old 2. The difference between these three questions, everybody, is that this function, and we're going to talk about this more in 2.4, this function right here is not a continuous function at integer values such as c. So we had to really pay attention to what those two answers were. But this function is continuous at a non-integer value like 2.6, so it wasn't that difficult just to read the graph and realize that f of 2.6 was just equal to 2.